Okay, so this is a new talk. It's the first time I'm doing it, so I really appreciate some feedback afterwards. So this is the universal architecture diagram. Okay, and when you see this diagram, there's a keyword here: service A, arrow, service B. What does this arrow mean? Okay. This is actually a distributed system. Okay, when you have one service call another service, two services is enough. You got a distributed system on your hand. And handling a distributed system entails many complications and things that you need to take care of. If you have hundreds of services or microservices in production, it makes things more complicated. And if you do it at scale, it actually now becomes more interesting. This is, just for example, this is just the catalog service that we have in Wix e-commerce system. Okay, this is what needs the services that need to run the catalog service. So, hi, my name is Aviran. I'm the head of engineering for Wix.com. I am a father, and I have a wonderful wife and 3 wonderful children. I also have a cat and a dog that thinks that the cat is for his amusement. This was my first computer. It had a whopping 64K memory. When you actually started the computer, the Dragon 64, you only had 32K of memory. Because if you wanted the 64K, you have to hack it. You have to run a special command to get the full 64K memory space. Because who needs more than 32K, right? I've been around for a while. I worked, this is just some of the places that I've been. I've been in large companies like Lockheed, consulting for Indeed, startups, founded my own startup, which failed, like 90% of all startups. And eventually I ended up in Wix. Raise of hand, who heard about Wix.com? Okay. So for those of you who don't know what Wix is doing and why am I here? So Wix is the leading website building platform in the world. It helps people like my mother build a website without any technical knowledge. It provides all the tools for small businesses to add, to sell, to present their dreams online. Recently, we also added coding capabilities, so you can write. This is actually what serverless should be. You write your code, you write your backend model, your front-end model, you click publish, and it works. No need to deploy to any service, no need to package it, just click, and it runs. In numbers, so Wix has 120 million website builders, and we're adding about 2 million every month. We serve about 500 million users monthly. Those are the visitors to the wonderful sites that our users are building. We're running multiple data centers, multiple clouds. We're about 2,000 people. Half of them are in the R&D. So for the agenda today is some of the patterns that we use to operate such a large-scale system. So we'll talk about avoiding database transactions, how do we handle schema changes without any downtimes, read consistency, which is a challenge in a distributed system, and how do we deal with multiple data centers. Many products don't need to deal with multiple data centers, but hopefully when they scale and grow, when you have multiple data centers, that's becomes an issue. So let's get down to business. First thing on the agenda, how to avoid database transaction. Database transaction is actually the worst thing that you can do to your database. It's a very expensive operation on a database. It affects your scale. It affects your performance. And if you want to run a high-scale system, you would probably want to avoid it, especially if you run in a microservices environment where your databases are spread across multiple databases. So every service has its own database or its own table or its own responsibility. You want to avoid database transactions. So I'm going to show you a pattern that we use at Wix on how to save pages. So we have our HTML editor. So the use case is user comes and edits a couple of pages and then click save. So what do we want to do? We want, let's say, she changed 3 pages. And once she clicks save, we want either all the 3 pages to be saved or none. We don't want this intermediate state where 2 pages are being saved and 1 has failed. So how do we do that? We basically don't want to have a database transaction to make sure all the 3 pages are saved. We need to replace our database transaction with a logical transaction. So changing the pattern a little bit. So this is how it goes. So you go to the browser, you edit whatever you want to edit, and then you click save. Now, the client application sends all the pages to the servers. It's a cluster of servers, so it doesn't matter which server gets which page. It can be in parallel. The servers just save the page to a database. Every server that got a page just saves it to a database. Now, the response that is coming back from the servers are the page IDs of those saved pages. Now, how do I make sure all the pages got saved? The client that got the ID sends another request and sends a manifest of all the page IDs that consist of this complete document. In our case, it's a website, but a complete document. So essentially what I did, if some of the pages failed to save, then I don't get all the page IDs to the client, so the client will not complete the transaction. It's the acknowledge, signing the transaction. But if all the pages got saved successfully, I request the client to, okay, send me now this manifest which actually sealed the transaction. So when essentially what I did is we created a logical transactions out of 2 different databases. Okay, so I'm making sure that it's either all or nothing. If something fails, I may have some orphan pages, orphan documents in the database, but since I don't have any pointers to it, it doesn't really matter. Now, what happens when we work in multiple data centers? Usually you think about, okay, we'll have a master-master replication and everything should work fine. And write traffic can go to both data centers. Now, the funny thing about replications is that usually you get replication conflicts. Okay, if you have replication lags, or if 2 users try to write to the same record. Now, in case of MySQL actually have 2 strategies to handle replication conflicts. One is to stop the replication and have a DBA comes and fix and continue, or to just ignore the conflict. Both of them are not great strategies. Some other databases like React, for instance, you can write your own conflict resolution strategy. You cannot do it with MySQL. So the way that we can actually overcome it is making sure that we will never have any conflict. Okay? So what we did is we generate the IDs of the page is a hash based on the content of the record. Okay? So what we gain by that is we gain an immutable data. And in case we got a conflict, if the ID is the same, we can just ignore it because we know that it is essentially the same content of that record. So the strategy that we configured MySQL in this instance is just, yeah, if you have a conflict, ignore because we know it's the same content. So that became a non-issue. Okay. Second use case. So we're running MySQLs with hundreds of millions or sometimes billions of records. And if you want to make a database change, a database schema, it may take days or even weeks to actually run the database migration. And the last thing that we want to do is to tell our users, hey, we're down for maintenance, we need to do some fixes in the database, you wait for a couple of days. You all know this screen? So how do we do that without downtime? So essentially when you want to change database, we have three use cases. One is you want to add fields, then other is to remove fields, and the third one is that we actually want a complete schema change, or even migrating from one database, I don't know, from MySQL to MongoDB. So if you want to add fields, we actually have two strategies to do that. So we have two types of fields. One, it's just a metadata. So you got your old queries that run, and I just want to add some information that I want to store. And in this case, what we usually do is that we have every table, we have a column, we just hold JSON. JSON is pretty fast. It's really easy to work with, and you can just basically extend your relational database with just throwing stuff at this JSON. But the second type of field is actually you want to add something to your database that you want to index it. You actually want to query it. So if you want to query it, you need to add an index. Now, we don't want to make any schema change. So what we tend to do is just create a second table next to it and do a join by primary key. Index this field, do a join by primary key, which is very, very fast, very, very efficient way to just add more columns. Now, this works great until you add more and more like this, and it becomes hard to maintain, and we need to actually do a database change. You actually remove and do complete schema rewrite. We'll get to it in a second. The other use case is actually the easiest one. If we want to remove field, we just don't do anything with it, just don't use it in the code, and that's it. Don't touch your database. So let's talk about how do we do a complete schema change. When we want to do a complete schema change or migrate from one database to another without downtime. In order to do that, you have your best friend, and the best friend is called a feature toggle. So what we do is we plan a lazy migration, which is controlled by feature toggle. A feature toggle is basically an if statement in the code. If the feature toggle is open, then do the new code. If it's closed, then just use the old code. Now, feature toggle is not just a Boolean, right? It can be a state, and it can actually be controlled by how you expose the feature toggle. We use P3, it's open source. It's a system that controls feature toggles and A/B tests. You can get it yourself if you want. So we use it in order to slowly control and expose the migration process. First to employees or to QA or to whatever criteria that you want. It's not all or nothing. So let's go over the process. So in order to start, we need a new database. So we prepare a new database migration. So this is the old database with the fish, and we deploy a new database schema to the production. And we prepare the code to do a lazy migration, which is controlled by feature toggles. Okay, so we have this database in production. So the first thing that we do is do nothing. It's in production, the DBAs can work on it, configure it, do whatever they want. Once they feel, yeah, it's ready for the migration, developer goes and start controlling the flow of using this database. So the first step is testing your write path. Okay? We switch the flag, and now we start writing to both databases. We start with the new, and then when it succeeds, we write, start with the old database, and then we write to the new database. Now, once we start doing that, we're actually doing a distributed transaction. Okay? And we need to understand which one goes first. I already told you that you need to start with the old one, because the old database is still the source of truth. If you fail writing to the old database, you just fail the transaction. If you fail writing to the new database, you just ignore and log it, and you can investigate why did you fail. You let this process run for days or weeks. You check that you don't hold objects that are too large in memory. You check that the replication works properly. And you start filling up this database. If something goes wrong, you can simply switch the toggle back, delete everything, and start all over again. This is a non-destructive operation that you can do, because your source of truth still stays the same. Now, when you feel happy with your write path, everything works as expected, you flip the toggle again, and now you're starting testing your read path. Okay? What you actually do is reading from the new database and fall back to the old one. Remember, not all the data is in the new database. You read it, and you complete whatever you miss with the old database. Now, there are different patterns on how to do it. If you know that the key is there, you can try with the new and fall back to the old. You can do it in parallel and prefer the new. You can join records. It really depends on the query pattern. But the idea is that you start using your new database for the read path. You can then discover that you're missing some indices, or that you actually have replication lags, or any issues with backward compatibilities. Backward compatibility is a must at this point. Up until now, you just wrote. Now you're actually reading something with a new schema. And it's a distributed system. You actually also pass it along to other services. So they need to be ready for new fields, new data that may come out of this new database. Still, if something goes wrong here, you can always go back, switch the toggle again, go back, fix whatever you need to fix, and start all over again. You let that run, again, for as long as you want, a few weeks. And then you get to a very critical step in the process. You actually stop writing to your old database. Okay, you only write to the new database. Now, at this point, this is the point of no return. Once you do that, you moved your source of truth to the new schema, to the new database. Okay? It's not really a point of no return because you can always migrate, but it is much better that you will be very certain that at this point everything works as you want it to work. Now, this is actually a very good step because now what happens is you can actually start migrating your old database to the new one. Your old database is now in a read-only mode, so data doesn't change and it doesn't grow. So you can take your time, do it whenever you want. We actually sometimes don't do it, you just leave it as is. But if it bothers you, you can just do a lazy migration, migrate. Now the migration path is very easy. Once you're done with the migration, then you can get rid of the code, get rid of the feature toggles, and the last thing that you can do is take your old database, archive it, and walk away. Okay, the third use case, consistent read. So for this story, we have two players. Okay? We got an e-commerce store, and we got the store owner, and we got the store visitor. Now, when a store owner wants to update their product, they send a request to update a product. We go to the product service, it writes to the master database, it replicates to the slave. Remember, we're talking about system that we want to have at scale. We want slave databases to enable us to have more reads. Okay? The store visitor goes, we have a lot more of those, so we point them to read from our slaves. Usually, not an issue. Now, what happens if we want the store owner to read the product? Then she can do whatever the visitor did, go to the slave and read the product. However, sometimes databases get to have replication lags. So in this case, we get the store owner to get an inconsistent state. Actually, the things that she wrote, she actually can't read right now. So how do we handle that? Pretty simple. We just give her a different API. Okay, for store owner, we get a different API. You can get consistent product. And the this API, get consistent product, just go to the master database, so we always get a consistent read. These use cases are usually good when you have a read after write. If you don't have read after writes, it's usually not an issue. But if you have read after writes, usually with Mongo, it's a good example. If you have read after writes, you want to read from the master. If you're working in a single data center, this is not an issue. Usually not an issue. Where it is, when it does become an issue, is when you actually start working with multiple data centers. Multiple data centers are a problem. There is no such thing as a master-master replication, unless you're willing to pay with latency. For every write, you go to the secondary data center and verify that the write actually happened on the secondary data center. If you have 3 data centers or 4 or 5, this becomes an issue. So let's look on how we handle cross-DC replications and the things that can happen. By the way, how many of you actually work with multiple data centers? Oh, good, fair amount. So we're going to go over some strategies on what we can do. So let's define the problem first. So writes can go into two of the data centers. You get consistent product. From here, you go to the master DC. You get consistent product there. You go to this master database. Master applications. Everything works good until it doesn't. When you have a replication lag, and between data center, the chance of a replication lag is much higher than within this data center because we're actually getting out. It's a different networking, go over the internet. The services are not close. You have big latencies because it's physics and the speed of light between East Coast and West Coast, or UK and the US is a distance. At some point, we get into a replication lag. And we get to an inconsistent state. So some of the strategies that we have, in order to explain them, we need to go one level above into how a data center is built. So in front of all our services, we got an API gateway or a load balancer that can actually help us mitigating those issues. So what options do we have? Our first option is pin the API to an active DC. So we got our 2 data centers, and we define one as our source of truth. We don't want the consistent reads or the consistent writes to come to both data centers. We can enable this if we identify a replication lag, or if you feel comfortable and you don't have a huge scaling issue, you can do it constantly. So how does it work? When we configure, okay, DC1 is our master DC, and we get a read to our secondary DC, or what's that? Yeah, get consistent product. The load balancer just forwards the request to our primary data center. From there, it goes to the product service and to the master database, and we hope things will get replicated eventually. So this is one strategy. Another strategy that we can have is to actually separate the read and write services. In the microservices environment, this is actually a good pattern to have when you want to handle scale. So we got our product write service and our product read service. We still have our master DC, but now when we get consistent product, our load balancer actually goes to, or our API gateway forward us to the product write service, because it is configured to work with their master DC. In the previous use case, we had to configure 2 connection strings to 2 databases, and every API needs to know which connection string to work with. In this use case, it is actually simpler to just have one DB connection, the write service, which is responsible for all the writes and the consistency, work with the master, the reads work with the slaves. It's much easier configuration. Now, if we have a replication lag, our load balancer can be configured, okay, the write service is no longer active in this data center. It will just forward the request. Now, it's not on an API level, it's on a service level. Everything that goes to the write service will go to this master data center and read directly from the master database. Again, you pay with latency, but if you want to have consistency, this is something that the trade-off that we need to make. Our third option is to use SQL proxy. What does it mean? It means that we have a proxy in front of our databases that now the DBAs can control what database the service is connected to. So when we get the request, and we know one of the features of SQL proxy is actually to identify replication lags. And we can have a rule, once you have a replication lag, I don't know, bigger than, I don't know, few seconds, few minutes, whatever the use case is, we can automatically just change the pointing of the SQL proxy. It will just point it to our master data center. The service itself is not aware that this change was made because it is connected to the proxy. And the proxy just makes all the logic to which database I want to turn to. It actually also helps with the reads, because if we see that there is a big replication lag, we can also change the reads, and when we get the read, we can also move it to a different data center, to the master data center, because we want the eventual consistency to be eventual and not very far away in the future. Option number 4, the last one, I promise, is to have the client so just like we have our load balancers in our data center, we can actually take advantage of our client application, whether it's the browser or an app or whatever client that we have, and have it configured to work with 2 different data centers. So it can be host name, this one dc1.whatever.com, and this is dc2.whatever.com, and we can just send the configuration into the client, and the client will just forget product. It doesn't really matter, but for getting a consistent read, it will actually point to the master DC. This actually, it can work, but it has its issues, because if we want to shift traffic, then we need to reconfigure all our clients, and we not always have connections back to the client. So it's a possibility, but it's not something that we actually do too often or at all. So what we do at Wix, actually we do those 2 strategies. We do have separate APIs, and using the load balancer, we just proxy the request. And now we also have the SQL proxy for some services. It actually works very good, the SQL proxy. And that's it. That was short. So just to recap, Arrow means distributed systems. So we need to make sure that we're avoiding database transactions if we want to have a fast and scalable system. We want to handle database changes without any downtimes. Read consistency, it's something that we should take care of depending on who the client is, who the user that uses the system. And of course, we need to deal with data centers, multiple data centers that makes the consistency problem even more severe. And that's it. Thank you very much. Questions? No? So I'm right here. If you want to ask questions, I would really love to have some feedback. Oh, I have a question. Yes?
Thank you for your talk. It was quite interesting. Maybe I missed some bits, but about these replication strategies, how do you know that you should get consistent product requests and not get product?
How do I know? Okay. So how do I know if I need to do a get consistent product and not just get product? It depends who the user the user is logged in, and I know what types of operations I need to provide to this user. So in this use case, if I know this is the store owner that works on their own store, then I know that in the flow of, let's say, editing a product, I know that I need a consistent read. Okay, and in the case of a store visitor that just want to buy, I don't have to have the consistent read. It can be eventual consistent. So it depends on the identity of the user in the system.
Does it mean that one user will always have consistent requests?
Yes, it means that one user will always have a consistent request in their context. Okay, it's not that, for instance, in a multi-tenant system, not all the site owners will get consistent reads for all the stores. They will get a consistent read only for their store. Does that make sense? Yes?
You mentioned with the SQL proxy, when there was lag time, you could flip the switch and kind of go to the master data center.
Yes.
So how are you monitoring those lag times? And is there some kind of alerting mechanism that your team have, or how does that?
Okay, so how do I monitor the lag time in SQL proxy? It's actually one of the features of SQL proxy. It monitors the lag time, and we have it in Grafana, and we got alerts on it, and you can actually automate the switch. We don't automate it. We have manual intervention, but we do have alerts on it. But it's one of the features of SQL proxy.
So you get an alert and then somebody sees it and flips the switch?
Yes, and we get a lot. We can configure how long we're willing to tolerate the replication lag. Like if it's 1 minute, up to 1 minute, it's fine. More than 1 minute, then we get alerts. Yes?
Is there a danger with that system where your offload, where you've had load that was going to replicants, replicants get out of sync because the master is backed up and can't replicate quickly. You then offload all the data that was going to the replicants, go to the master, and you end up overloading that
Actually, yes. Well, the question is how do I offload the load from the replications? Actually, we replicate from a slave on the same data set, so we don't replicate from the master to a master. We replicate from a master to a slave and from a slave to a master. So that's how we offload the load from the master database. Yes?
So you show the get consistent product, but do you base any rise on this view of data? Because having consistent read doesn't provide you with consistency unless you have some sort of optimistic blocking, or you have users that only write as single user to a single aggregate.
We have the consistent read on the specific use cases for the user. It's not a consistent read on all the system. We tend to do an eventual consistent read for scaling and for users that don't need it, but just for those specific users and specific use cases for specific data that they request, only then we do a consistent read. It's not everything that is consistent.
Have a single user that actually writing data that they just read.
Yes, so we have the specific users that writes the data, and only they're getting the consistent read for their own data. They will get an eventual consistent read for someone else's data, just for their own data. Yeah, because we want to offload the load to many, many users. All right. So thank you very much. You can download the presentation there, and I'll see you later.